So this is the second part of memory interfacing with 8085 microprocessor. In last section, we have seen the internal structure of one bit of a memory element. What are the basic components present in a memory element, and what are the components required to access a memory device. We come to know that to access a memory device, we require address lines, data lines, and control lines. Address lines are basically required to address the particular memory element. Data lines required to transfer the data to or from the memory, and control lines are required to distinguish the operation like read operation or write operation, etc. In last session, we have introduced if there are multiple number of memory element present, how address lines are used to access individual memory element, like one memory with 4 registers like register 0, register 1, register 2 and register 3. To access individual register, as there are 4 number of register present, so to access this memory device we require 2 address lines, namely A0 and A1. It is related in the fashion that if there are n number of address line, it can access 2 to the power of n number of memory element or memory locations. So depending on the memory location, we have to choose the address lines appropriately. So now let us expand the memory, because sometimes we require to connect multiple number of memory chip with the same system. So how basically they can be connected, we will be knowing under this session. First, in this picture we have taken a very small memory, like consisting of only, in case of first one, it has we need to constitute R0 to R7, R0 to R7, that means 8 memory elements. That is, one memory constitutes of 8 number of registers, and how it can be formed with the help of 2 memory device, each of which constitute of 4 number of registers. Here it is shown that this first memory device R0 to R3, that means 4 register present. In second memory, it has also 4 register present from R4 to R7. As we know that to access 4 number of register, we require 2 number of address lines. So A0 and A1 both are connected with the memory device to A0 and A1 line. Then how can we distinguish each of the element? For that we need to use a third address line, namely A2. And how A2 is connected? Here it can be shown A2 is connected directly with the memory chip 1. If we consider this is memory chip 1 and this is 2, so A2 is connected with the first memory chip directly, whereas with the second memory chip through a NOT gate. So it is observed that if A2 equals to 0, then first memory is going to select, because chip select signal of the memory is active low type. So when A2 is equals to 0, then first memory chip will be selected. Similarly, when A2 will be equals to 1, then through the NOT gate output will be getting 1. sorry, so we'll be getting 0. So at the time memory chip 2 will be selected. So address range of the memory present over here will be A0 and A1 will vary 00, 01, 10 and 11, but A2 remain equals to 0 for the chip 1, whereas for the chip 2 A2 will be equals to 1 throughout, whereas A0 and A1 varies from 00 to 11. That's how we can expand the memory. Similarly, in another picture, it is shown that if we have multiple number of address lines, how we can connect with the memory. That means with respect to the available memory, if we have more number of address lines, then single NOT gate will not be sufficient. For that, we need to use NAND gate, which is shown over here, or we can go for a decoder circuit to use the additional lines. Here we can observe that each of the memory element, if we name it as say 1 or 2, each of the memory having 4 number of chips, 4 number of registers, and for 4 number of registers 2 lines are sufficient. But as we have provided with the 4 number of address lines, 2 as usual connected with the memory chip in the form of A0 and A1, but additional 2 address line A2 and A3 are connected with the chip select line of the memory, through a NAND gate. And as for the circuit, the chip select will be enabled if A2 and A3 both are equals to 0, 0. If A2 and A3 equals to both are 0, 0, because in front of NAND gate there are 2 NOT gate present. So in this particular case, the address range will vary from 00, 11 to 0000 or 0000 to 0011. Similarly, in case of memory chip 2, where also we can observe 4 number of register element present, 2 address lines are insufficient. Here, to enable the chip select line of the memory, A2 must be equals to 0, whereas A3 should be equals to 1, because in front of the NAND gate A2 line a NOT gate is present. That's why in this case the address range of the memory varies from 1000 to 1011. That's how the additional address lines can be connected with the memory chip. Now come to the real problem, where usually we have provided with the not only 4 or 8 number of register, but at least 1K, 2K or 4 kilobyte of memory to connect with the 8085 processor. In this particular picture, both RAM and ROM, EEPROM basically, picture has shown to perform any programming, we require both the ROM device and RAM device to be connected with the 8085 processor. It is known that RAM, basically random access memory, where data read and write both possible. In case of ROM, data only can be read from the device. That's why it can be observed that with the ROM chip, RD bar signal, RD bar control line is only connected, whereas with the RAM, both read signal as well as write signal is connected. Both the read signal and write signal is connected, because from the RAM we can do both the operation. That means either we can store the data into the memory or we can read the data from the memory. But in case of ROM, only read signal is there, because it is only read operation is only possible. Chip select, obviously to select to enable the whole chip, to enable the whole chip select line must be enabled. So with every memory device, one chip select signal is present, and usually this chip select signal is active low time. And depending on the amount of memory, number of address lines present. In first picture, it is observed that 2048 cross 8, that means it is a 2 kilobyte of memory, and 2 kilobyte of memory, 2k means 2k kilobyte of memory means 2 to the power of 11. So here, to access this memory, we require 11 number of address lines. So with the RAM of 2 kilobyte length, A0 to A line, that means 11 number of address lines are connected, as because each location can store 8-bit data. That's why 8-bit data lines are also present over there. Similarly, in case of ROM, it is a 4 kilobyte of memory, that is 2 to the power of 12. 4 kilobyte means 2 to the power 12. So 12 number of address lines present over here. So depending on the memory size, we need to calculate the number of address lines are required to access the memory. So overall, we come to know the fact that 8085 processor, when it is connecting with the memory element, we required 16 address lines, among which 8 address lines, higher order address lines, are directly connected, that is the A8 to A15, whereas lower order address lines A0 to A7 are obtained from demultiplexing the AD0 to AD7 line with the help of 74373 device. And for this demultiplexing, this ALE signal is very important over here. At the T1 cycle of any operation, basically ALE signal goes high, and it helps to latch the addresses onto the 74373 latch. And once the memory is selected, once the memory location is identified, data from that memory is transferred through the data lines to or from the memory. So things to be remembered over here, that in case of multiple number of chips, most of the time single NOT gate will not be sufficient, because there may be many number of unused line present. That means the number of lines connected with the memory and number of lines coming out from the microprocessor may be unused. More than one number of address lines may be unused. So single NOT gate will not be sufficient. In that case, we may need to use the multiple number of NAND gate or decoder circuit like 3 to 8 decoder, 2 to 4 decoder, etc. to connect with the memory chip. Here one diagram is shown that where we observe that multiple number of memory is present, like memory 1, memory 2, memory 3, memory 2, memory 3, memory 4. So each memory has differentiated from other by its chip select line. So how chip select line is connected with the address line is very crucial. Depending on the chip select line connection, address is determined. So here it is observed a 2 to 4 decoder is used to connect with the memory 1, 2, 3, 4. So as there are 4 number of memory present, as there are 4 number of memory chip present, for individual chip select line we require 4 individual signal, and that can be obtained by decoding 2 address lines. Here A11 and A12 2 address lines are connected, 2 address lines are present, that is going through the decoder and generating 4 number of signal in the form of O0, O1, O2 and O3. So whenever these two lines will be 0, 0, at that time O0 line will be activated. This is the active low type decoder. So chips memory 1 will be selected when this is 0 and 1. At that time O1 will be enabled. So memory 2 will be selected. Similarly, in case of In case of 1, 0, O2 is going to be enabled and memory 3 is selected, and finally if we place the signal 1, 1, then O3 line will be activated and memory 4 is going to be selected. So if there are multiple number of memory chip, then it is always better to use any decoder circuit for the selection. So overall picture is this. Here 8-bit data lines are connected with the data lines of the memory, and 16-bit address lines are connected with the address lines of the memory. And if there are any unused lines, for example there 1 kilobyte of memory is present, so as 8085 microprocessor having 16 address lines, the 6 address line will be unused. Those 6 address lines are to be connected with the chip select signal of the memory. So that's how the complete memory chip is interfaced with the 8085 processor. And control lines, it is discussed in part 1 that how to generate memory read signal and memory write signal with the help of NAND gate. So that memory chips, memory read signal and write signal are to be connected with the read line and write line of the memory chip. So that's how the memory is connected with the 8085 microprocessor. Now let's take one real-time problem and take different number of address lines and try to observe how that can be connected to access the memory. Here 2 memory chip is considered, 1024 that is 1 kilobyte of memory and 4096 that is 4 kilobyte of memory. So first, interfacing of 1024 1 kilobyte of memory with the help of 10 address lines only. It is obvious that to access the 1 kilobyte of memory we require 10 address lines. For accessing 1 kilobyte of memory we require only 10 address lines, so no additional lines we are considering here. So if there are 10 address lines for selection of register element 0, all the signals from A0 to A9 will be equals to 0, and to select the last memory element, that is register element 1024, all the address line should be equals to 1. So if the address lines varies from all 0 to all 1, subsequently the registers of the memory will be selected. Thus the total address will vary for this memory from 00 to 3FF in hexadecimal. Hexadecimal, if we consider hexadecimal value, so it will vary from 000 to 3FF. This is a simple diagram. Here, as we have considered no other address lines, so chip select line directly grounded here. That means chip is always enabled without depending the address line. Depending on the address line, chip select is always selected or enabled, and read and write line depending on the operation will be enabled by using MEMR or MEMW control line. Now, if we consider one additional line, that is interfacing of 1024 with 11 address lines, then what to do? As usual, with the memory chip A0 to A9 lines will be connected to select the individual memory element or individual registers. That is obvious, but the additional line we need to connect with the chip select signal of the memory. We need to connect the chip select signal of the memory. As A10 line is directly connected to enable the chip select, that A10 line must be equals to 0. A10 line must be equals to 0. So here also A0 to A9 will vary from all 0 to all 1 for the selection of the first memory element to last memory element, whereas A10 line will remain fixed at 0. So in this case also address range will be 30 to 3FF. And we can also connect one NOT gate in front of the A10 line, and in that case A10 line must be equals to 1. To enable the memory chip, A10 line must be equals to 1, because we know chip select is active low type. So in this case, the address now for A0 to A9 it will remain same, varies from minimum value to maximum value. So as A10 becomes 1, now the address will change. Its first address will be 400 in hexadecimal to 7FF, that is the last address of the memory will be 7FF. That's how the once we change the address value, how address lines value, how the address of the memory is also changes is shown here. Now if you use 12, that means two extra address lines for the selection for the interfacing of the same memory device. So now this time two address lines which A10 and A11 cannot be connected directly with the CS, and single NOT gate will not be sufficient. So we have to go for the either for a NAND gate or for a decoder. So in this diagram a NAND gate is used, and in front of the NAND gate two NOT gate are also present. That means to enable this chip select, A10 and A11 must be equals to 0. A10 and A11 must be equals to 0. And remaining address lines A0 to A9 varies from lowest value to maximum value. So in this case the address as A10 and A11 is 00, so it will be 000 to 3FF in hexadecimal value. Here one different arrangement is shown, that is in front of the A10 address line no NOT gate is present, so its value must be equals to 1. A10 value must be equals to 1. A11 it remains same like before, so A11 should be equals to 0. So this time the address of the device changes. Minimum lowest address is 4002, highest address 7FF. That's how address line varies. So here it is shown all the different combinations. As A10 and A11 line, it can either be 00, either be 01, or 10 or 11. 4 different value it can take. So in all the different situation, so address range varies depending on the chip select signal. How the chip select line is connected with the unused address lines, accordingly the address of the memory device varies. So in the last diagram, it is shown that if we are going to connect this device with the 8085 with having 16 address lines. In previous circuit, we have considered if there are only 10 lines, if there are 12 lines or 11 lines, but actually in 8085 microprocessor there are 16 address lines present. So if we consider all the 16 address lines of the device, so obviously there will be 6 unused lines present, and we have to connect all these 16 address line with the chip select, because A0 to A9 are already connected with the memory device that is used to select the memory element, whereas the unused line A10 to A15 are used to enable the chip select line. So in this particular picture, it is shown that all the lines are connected with a NAND gate through NOT, so the signal must be equals to 00. All the lines A10 to A15, all the lines must be equals to 0, and in that case only the chip will be selected, and for this purpose the memory address will be varying from 4 zeros to 03FF. If we consider the 16 address lines and it is presented in hexadecimal value, 4-bit hexadecimal value, so address changes from 4 zeros to 03FF. Now in case of 4G96, that means 4 kilobyte of memory, we know for 4 kilobyte of memory, it is 4 kilo means 2 to the power of 12. 12 address lines are required. That is 4 number of unused line will present, and that 4 unused line can be used to connect with the chip select lines. 4 address lines through a NAND gate can be used to connect with the chip select. Here A12 to A15 are directly connected with the NAND gate. No NOT gate is used in before. So the chip will only be selected if A12 to A15 are all at logic 1. Then only the NAND gate output will be equals to 0 and chip will be selected. So in this particular case, A0 to A11 varies from the minimum value, that is all 0000 to all 1111, whereas A12 to A15 remain fixed. So for this case, its address range become F000 to 4F. This memory, 4 kilobyte of memory, if we connect with the microprocessor 8085 having 16 address lines, and A12 to A15 keeps at logic 1, then the address of the memory will be F000 to 4F. So depending on memory given to us, we have to first identify how many address lines are required to select the memory element, how many address lines are required to select the memory element, and how many address lines are unused remains after that, and those address lines we can connect with the chip select either through a NAND gate or either through a decoder circuit. So with this, it's conclude that any amount of memory, that is maximum of 64 kilobyte, obviously because of 16 number of address lines only, 8085 can access 64 kilobyte of memory. We can connect it with the processor, and depending on the circuit diagram or connection diagram, we will be having particular address. Thank you.